This video explains the example for parallel reinforced concrete T and L beams. T beams and L beams are casted internally with the slab span 666 millimeters. Are spaced at the center as shown in the figure. The load superposed on the slabs are dead load 0.6. So on this slab dead load is 0.6 kilopascals and live load on this slab is 3 kilopascals. Showing your answer on appropriate line diagram, calculating following to be resisted by the edge beam. So those are edge beams whose section is shown shaded. We need to calculate dead loads, live loads, and strength limit state for shear force and bending moment diagram. So we're going to focus each questions one by one. Now the first one, we'd like to calculate the dead load. Now for the case of dead load, we can draw the diagram. That is a beam, and if I that is the edge beam, which is 6600 millimeters span. So if I show it this one, so that is the edge beam, which is 6600 millimeters. Now it has a two loading coming on to this beam. One is uniformly distributed load and another one is this triangle distributed load. So uniformly distributed load is coming from this portion, and a triangular load is coming from this shape of this 30-degree pitch geometry. Now first of all, I can get this geometry from the original figure. So if I have this shaded T beam, if I draw it here on this end, I can show it that is 1200 millimeter, 120 millimeter, which is 120 millimeters, 400 millimeters, which is thickness of this 400 millimeters, and then calculation of 1400 millimeters is a little bit tricky, but we can see here this is 3200. So 3200 take away 2, which is 300, take away 200 here, which is 2800, and half of 2800 is 1400. So basically we are taking this distance, which is 2800, because we have 200 here, take away 400 from 3200 give us 2800, and half of 2800 is 1400 millimeters. Now 1087 millimeters is the height in the middle of the height is from 1000 plus the height of this in the middle portion. So these calculations are given here. So we have this thousands millimeters plus 300 divided by 2, and this 300 coming from here. So we have 150, which is 150 30-degree triangle, and we are looking for this one. So that is 150 times 1030. Add them together, we get 1087 millimeters, which is 1087 millimeters. Once we get this geometry, we can calculate the dead load. Now the density of the reinforced concrete is 25 kilonewton per meter. It's given in the questions. If it's not given in the questions, we can check it on table A1. Table A1, where we have a concrete with 0.6 reinforcement. We have 24 and we need to add 0.6, so it's a 25 kilonewton per meters. So 25 kilonewton per meter. So the equations to calculate the UDL load is the density times the perpendicular area. Now let's check this area first. So let's talk about this area first. For this area, we have 1.4, which is 1.4 meters times 0.12 meters times the density. We have 4.2 kilonewton per meters. Second area, we can take this area, which is 1.087 meters times 0.4 meters. That's the perpendicular area times the density of the concrete is 25 kilonewton per meters, which give us 10.87 kilonewton per meters. And in the questions, it has given the 0.6 kilopascal. So in questions, it has given 0.6 kilopascal. That is the dead load on this flat slab. So that is 0.6 kilopascals. Converting pressure into the UDL load, we have a pressure times the perpendicular length, which is 0.84 kilonewton per meter. If we add 4.2, 10.87 and 0.8, we get 10.9 kilonewton per meters. Now this is the UDL load. This is 10.9 is that is 15.9 kilonewton per meter. So that's the magnitude for this uniformly distributed load W1. So W1 is 15.9 kilonewton per meters. Now the next one, we need to calculate this triangular loading. Now for this non-uniform distributed load triangular loading, we have this 6600 millimeters. So that is your 6600 millimeters, and we have this height which we can calculate by taking the half, so which is 3300 times 1030, so 1905 millimeters. So we can say this 1905. So that is basically this height, 1905 millimeters. Now once you have this geometry, we can have density times perpendicular area. Density is 25 kilonewton per meter cube, and the perpendicular area is 1.905 times 0.4. 0.4 is coming from this thickness of this portion, which is 0.4 meters, and multiplication gives 25 times 1.905 times point gives 19 kilonewton per meters. Now in this case, this is the UDL load, and it has a magnitude of 19 kilonewton per meters. So this is the answer for the first questions, finding the uniformly distributed load and non-uniformly distributed load in the form of kilonewton per meter. Thank you very much.